Okay, so hopefully we can have more smooth experience with today's presentation. Okay, so we have, I think we can just a little bit review. So indeterminate forms, the basic concept is whenever you find 0/0 situations, okay, when you have a limit, okay, and when you take the limit and input the x inside the functions, so you have a rational function f/g, and when you evaluate, it's a 0/0. Okay. We call this situation the form. We call it indeterminate, which means we are not sure that is it going to be 0 or is it going to be 1 or is it going to be infinite. There are many possibilities. Okay? So that's why we invent a method that's called we call this is the Orbital Rule. Okay? I think I mentioned that at some point when both functions have 0, okay, at some point here, nearby this point, if we are going to write or sketch the tangent, if we zoom in these nearby positions, they are certainly the same as our tangent. So we can take that as a proportion. If we compare the f with g, it's actually comparing the derivative of f and g from the picture. And then from small observations, if we are looking on how to prove, if we take the limit f/g, and we know that when f at a and g at a, they are both 0, so we can actually, why we are going to have this, because it's 0, so we can add or minus, because it's, if we are just letting them as the equation is, it's going to be 0, right? But let's just write minus f and minus g, and then multiply both sides, both the numerator and denominator with 1 over x minus a. And by doing so, okay, so if you are confused, well, yeah, we can add this minus, because they both are 0. They both are 0. Okay. And then this form we can rewrite like this, and if you remember that this is the limit definition of the first one is f, the second one is g. Okay. So by the end of the equations, we can see that the limit, okay, of f/g as x approaching a we can take the rule, the Orbital Rule, and then we can differentiate f to f prime and differentiate g to g prime. Okay, so we can have f prime a and g prime a at the end of the equations. Okay, if this is not 0/0. If still when we take this derivative, if we input a and still 0/0, you can still derive. You can still derive how many times, as many as you can, as long as at the final form it doesn't have 0/0. So you can do it many times. Okay, now we have this as our basic concept for indeterminate forms. So whenever you have 0/0 or infinite over infinite, because they have relations in 0/0 and infinite over infinite, because infinity, we can get infinite because of limit of 1 over x, for example. If x is going to approach 0, it's going to be infinite. So it's kind of, they are reflecting each other. So they have the same or similar properties. So we call those form indeterminate forms. Okay, this is just the requirement. Okay, the requirement. Let me write this as requirement. Okay. For example, you have ln x over x minus 1, and you have limit as x approaching 1. So when x approaching 1, it's going to be ln 1, 0. And then 1 minus 1 is also 0, so it's 0 over 0. So you can take the Orbital Rule, which means that ln derived becomes 1 over x. And x minus 1 derived becomes 1. So it's going to be 1 over x. And when you try to take the x inside, 1 here. 1 over 1 is just 1. And so we finish the results. Same thing over there. You can derive and you can get the results. Okay. And then we have another forms which we call the indeterminate products. Okay. This is when we have this 0 multiply with infinity. So 0 multiply with infinity. We call this indeterminate product. This happens when, for example, you have x ln x. If you put 0 inside, x becomes 0, but ln 0 is infinity. Remember the ln? Okay, that's one of I'm suggesting you to have to know some of the essential graphs like ln e to the x, 1 over x. I think this tree is kind of I think essentials. Aside from like polynomials like the quadratic, the cubic, and I think the square root of x, I think that's also essential. So what we can do from this limit is, although this is 0 and infinity, the idea is to make either 0 or either this infinity. We are to take force to make one of the functions going down. So we imagine that this form can be written as these two functions f and g. We can either take f and the denominator become 1 over g, or we can take the 1 over f as in the denominator. Okay? So the idea, why we are doing this, because when we are taking this down, we want to force out. We want to force out and makes the 0 infinity become 0 over 0 or infinite over infinite. So we are taking back to our original action, okay? That the indeterminate form is 0 over 0 or infinite over infinite. Okay, so we are taking this, for example, ln 1 over x, because I think it's better to have 1 over x down rather than ln x, right? Because 1 over ln x is, if you think using derivative, you must think which one is better to derive. Okay? And when we look on the form is infinite over infinite, take the Orbital Rule, and you have this result. And you can, I think you can finish this simplifying calculations, and you get the result as 0. Okay, another one that we have. We have another one is we call the indeterminate difference. This is when we have infinity minus infinity. Okay, so if limit as x approaching a and limit. Then and if we think fractionally by logic, if this is the results, okay. So you have the limit of f that is infinity, you have the limit of g that is also infinity. And what will happen if you have limit and then the equation is f minus g? Well, how do we write this? Result, is this equal to? Equal to? Okay, can we make this 0? That's the question. Okay, no. So this is not equal 0, okay? Why? Because remember, this infinity is an idea. It's an abstract, it's a symbol. It's not a number. It's symbolized the number that is large, which you cannot really measure how much. So that's why it's an idea that it isn't going to be, or it isn't going to be calculated in any way we are going to calculate. So we do not calculate this as 0. Okay, do not. Okay. So what we can do here is, again, the idea is still the same as previous method. So whenever you find this, you need to find a way to make this f and g. Maybe simplify the form, maybe take some rationalization, factorization, any method that you can make some simplifications, and then try to look on how to make the 0 over 0 situation. So for example, okay, we have this. And if we take a note that if we imagine this is as f and g, both f and g, if we take the limit that is x going to approach 1, they both will give us negative, infinity, negative, infinity. Okay. So this is an indeterminate difference, infinite minus infinite. So what we can do now, we can start by to take the or to combine this together and see whether we can simplify the form. Okay. Okay, when we are having this combined together, we check the limit. The top one is 0, and the denominator also 0. So it's 0 over 0. So we can do the Orbital Rule. So we take the Orbital Rule. Usually Orbital Rule has this LH. So to take notes that we are doing Orbital Rule. So this will be 1 minus 1 over x. And this will be x minus 1, 1 over x, plus ln x. And then some simplifications. Let's simplify. So we check again. We check 1, 0. Check 1, still 0. Right? Still 0. So what we're going to do? Take orbital rule. So take it slowly. We can do as many as we can. As long as it's 0 to 0, we can do L'Hopital rule. Okay. So we take L'Hopital rule. Okay. X ln x is going to be 1 plus ln x. So if we take the limit, we are going to have 1 over 2. Okay. Okay, now we take another slide. If we have limit as x approaching infinity, e to the x minus x. And sometimes you don't really need to calculate or evaluate the limit if you can somehow explain in a logic sense how we can compute it. So limit as x approaching infinity of e to the x minus x. If you're just thinking on this infinity going to have evaluation both of e to the x and x, it's going to be infinite of minus infinity, of course, right? But if we think just think, maybe we cover this limit, okay? And we are thinking on how the graph looks like on e to the x and x. And if you remember, I think I have explained a little bit on e to the x behavior. Okay? So if I take the x squared and 2 with power of x, which one is going to be increasing faster, left or right? Still not sure. This is how actually we have to take some time to think, or how to make ourselves critical, how to increase our critical thinking in solving some problem. Yeah, I think x squared, you can imagine how it looks like. But how about this exponent? And why it's called exponent? If someone talks to you, maybe some other professors, or maybe from the news, or when you read some books and they explain to you, it's increasing exponentially. Do you understand what they mean? Exponentially. Someone, you have an idea, I think.
To the power of something.
Yeah, to the power of something, but what does the implication mean? What's the implication of exponential?
Multiplying by itself.
Not multiply like that. If you compare this, the easiest way to imagine, try some number. Try 1. Okay, still not really going to see the difference. Try 2. Oh, it's the same. 4, 4. And 3. Well, it's 9, it's 8. 6 is bigger, right? Then 4. Well, it's going to be the same again. Interesting, right? Take 5. 25. 52. Take 6. 6. 6. 64. So which one's bigger? Yes. Okay. Simple. So when you heard someone says it's the numbers is increasing exponentially, which means you can imagine like you have 2 and it's double every time. Like you imagine like the population is double every time. So when you have e, it's actually double every time. So actually it's going to be faster than this x. And if you can put your arguments like that, you can just take this equal to infinity. Okay? It's reasonably logical. And if you want to verify, we can take this limit. Just take the x out of equations. And this going to be, so as x going to be infinity, then e to the x over x also going to be infinity. So this equation will still grows large, because this e is going to be increasing, largely, sufficiently large if you compare with just x, just the linear. It's a small number in the linear, right? So you can take this as infinity. So we know that from here it's actually exponential will grow faster. Okay, another section is called the indeterminate powers. I think this will be the last section on the indeterminate forms. So this form is going to have a power. So the limit, you have f, and it will be powered with another function g. Now we have several possibilities. If this is 0, and this is also 0, then what we will find is this will be getting 0 with power of 0. And then secondly, this will going to be infinite with power of 0. And then the third one, so we have 3 conditions. Now this is an interesting form. If you look on the forms f with power of g, okay, you have limit as x approaching a. So in indeterminate powers, we have 3 possibilities. Okay? The first one, you have the f is 0 and g is 0. So you will have 0 with power of 0. And I think if you can make out some logic sense on this 0 with power of 0, I think it's going to be, is it going to be 0 or is it going to be 1, right? They are going to compete which one is going to take the result. But actually, because that is the case, this becomes the indeterminate form also. And then the second one is also similar, but instead of 0, we have infinity. So when we have infinity and we have the power 0, will it be 1 or will it be infinity? It's also indeterminate. Now the one thing that is really surprising is 1. 1 with power infinity. Of course, if you think directly, 1 with power of any numbers is 1, right? Or no? Okay. If you take 1 with power of some, maybe if I take 1 to power of 20,000, is it going to be 1? 1, right? But here, is it 1? Okay, now this is the constant. This is not the same. Now what we are going to do here is this infinity came from the limit concept, and we have the limit concept here, right? The limit concept here. So what actually we are dealing with is This is actually, if you think on, maybe I'll give you what kind of example that gave you 1 with power of infinity. Something like probably a limit as x going to be approaching infinity. And then this is 1 plus 1 over ln x and with power of x. If you look on this form, this is precisely getting the form of 1 to the power of infinity. Okay. But because we are having infinity in the power form, it's becoming indeterminate. It becomes indeterminate. It seems that this is going to be 0 because it's having infinity, and then 1 over infinity and limit is 0. But still, we are having a condition that we are not really sure what is happening here. Is it going to be 1 or is it going to be something else? But I think if you take closer look on these 3 possibility, there are 1 combinations that not really included here, which is the combinations of 0 and infinity. But do they exist? They exist. But they are not infinite. They are not infinite. So except, so this is 1 exception. Okay, we will see through maybe after some time today what is this form means. Okay, now let me give you what we can do if we encounter all these conditions. For example, you have a limit as x approaching 0 from the right. The function is x with power of x. Okay, now if we observe, this is 0 with power of 0, right? 0, 0 situations. Okay, so now the idea, if we have 0 on the power, the concept, we want this 0 to be in the front. We want this x not in this power, but rather beside the other x. How we can do that? How we can take this down? That's the question. Okay, any idea? How do we make this power going to in front of this? How do we make that happen? Any idea? Any idea? Very good. Oh yeah, take ln. But there's a problem with take ln. It's half correct, half correct. If we take ln, of course, this is going to be the front. But can we add ln? Okay, let me just finish a little bit and then we can have short break. So ln means that this is log, but in the basis of e, right? Ln, which means that it's related to e. So if we have some number e and we take ln as its power, for example x, is this equal? Equal, right? This is one of the property of the log and e. So we can take the ln, but we need to have the e. So we can take this into the forms of so that we can take this x to the front. So I will we'll have a short break and okay, I think we can continue a little bit. So the idea for all indeterminate powers, we have this x with power of x. We are going to force this x right down, and what we can do is we are going to define this at e with power of ln, and we make this into our functions here because this is literally just another form of this x. Okay? If you remember your algorithm, okay, this means that e log e x. Okay, e can be anything. Like we have 3 log 3 is going to be the same as e, and the same e is going to be the same with this x. So when we are going to involve this e with power of ln and we put the function inside those ln, then this will become, we can solve further and take down the x, and it's become x ln x. And because it's e, and remember, e is not a variable, it's a constant, it's a number. E is a number, 2.78 something. So because it's a constant, we can think that the limit, it will affect the variable, right? So we can take the limit inside of the function. So we have e and then limit. Okay. And then you can solve the limit. And remember, because we have e, don't forget to invite e. So sometimes, when we are dealing with this, sometimes we can take, or we can separate e and function because sometimes maybe some students think it's too much to write. So we can just imagine like maybe we take the f of x as x to the power of x, and then this is ln, or maybe y. I think we better y, and then ln y is ln x to the power of x, and then you can take ln y, x ln x, and then you can solve this and attach the limit. Okay, so we attach the limit. This is another way that you can also think. It's the same, similar process. The difference is we are taking it separately. And we can solve this, but remember that this solution, this result, is still in ln. So we are going to have y. So we need to take again the e. But the mistake that happened on the left side is sometimes you forget to take the e. So if you finish this, you find some number, but you forget to put the number inside the power. You forgot to include e. So for example, x ln x, we already did this before. It's 0, right? 0. Let me just go through a little bit. Where is it? Here. It's 0. 0. So we take the forms, make it into infinite over infinite. the results will be 0. But this is ln y, right? Limit of x but then we need to take with e, so e with power of 0, this is 1. So if you take the left method, you take separately, you get the result of x ln x, you get 0. Don't forget to take the e. So you take the limit, this is y, and then this will be e with power of 0, this is 1. So the general form, if you have f of x with power of g of x, you can take the e and then g of x ln f of x. And also, if you observe that if we solve this kind of indeterminate powers, we will receive the ln, right? And sometimes it's not as simple as this x of x. Sometimes it has to be more complicated forms. But since it still has the ln, when you do Orbital Rule, probably it will have the indeterminate powers like this, like 0, infinity. Okay. So when that's happened, we are going to involve the previous method in which we are going to take this x going down. Right? And I think, let me just give you an example. So this is 1 plus ln 4 over x with power of x. This is 1 with power of infinity. And similar with the previous one, but since it's going to have, I think, a little bit complication here. So if you take the e and then ln, if you think it's too big, then I think you can simply separate like this function as y. So maybe you can write like let y equal 1 plus ln 4 over x with power of x. And then we can solve this, and we take the ln, we take ln y, and then x ln. And it's actually similar forms. Okay, if you see here, this is going to have infinite and 0, and don't forget to take the limit. Take the limit, both sides, Okay, so because we have ln, like I mentioned, like in the previous one, if we have ln, actually we have these two forms, like x and ln some functions here. Okay, so let's say this is f and g. Of course, one of them should be going to be our denominator, right? But which one? But since ln is easier to derive, right? Rather than if we take ln into 1 over ln, it's going to be more difficult. Then we are just taking this x going up. Right? We are taking that x, so ln, and this will be 1 over x. And now this will be 0, this will be 0, so 0 over 0. ln, what something constant over x is 0, 0, x is infinite. ln 1 is 0, 1 over x with limit, this is also 0. Okay. So we are going to take the Orbital Rule. So we derive the ln. So this will be ln 4 over x squared, okay. So we cancel this too. One plus ln 4 over x. And we can directly answer that this is equal with ln 4. But remember, this ln 4 is still ln y. Okay, so ln y, our limit of ln y is ln 4. So limit as x approaching infinity of y is e with power of ln 4. This is 4. Now, I will add additional notes. Suppose f is a positive function. If limit and limit proof limit equals 0. Okay, now if we look on the functions and the results, if we take the limit, we are going to have 0 with power of infinity. As I mentioned before, that this is not indeterminate forms, and why? So we are going to prove that this will be going to be 0. So first, let y equal f of x, g of x. We are going to have some simplification and some rewriting forms. So take ln y, and then take both sides ln. Okay, since we define the ln or the f as a positive function, right, from the arguments at the very beginning of the statement, then the ln is defined, right? We can define the ln. And for example, if we can just illustrate the ln, if you remember ln x is like this, right? When it's going to approach 0, it's going down, right? And our f of x is also similar. Okay? It's also similar. Let's say this is our ln f of x. It's going to infinite amount, but in negative direction. Now, if we take the limit, both sides of these equations, okay, we take the limit. So we take the limit of ln y for limit of g, as mentioned in the statement, it's going to have infinite, right? So it's going to infinity. But ln, as you may see from what we have here, when we are going to approach to a some number, it will going to infinitely negative, right? So this will be having a negative. Or let me write limit okay, but since it's infinite, but it has a negative, so it's going to have it's said that it's going to have a negatively large infinity, right? It seems, okay, it seems. Okay. So we can going to take this as negative infinity. But what does it imply? What does this negative infinity? If we remember, what we have is e with power of x, okay? Because we can convert this into e with power of this. So limit. We take the limit inside. Okay. Now what is happening when we have this is negative infinity? This will result e with power of negative infinity, in which if you can visualize, this is equal with 1 over e with power of infinity. And if you can imagine that through the graph of e, this will result 0. So if we take the some visualization of e, let's say this is e to the x. And this is e with power negative x. So if we imagine this e to the x, and we have e with power negative x, you can imagine when x is going to have negative infinity or x going to have positive infinity of both cases, you will see that both going to have 0, going to be 0. One be going to the left, right, both going to have a 0. So when we have e with power of negative infinity, this will be, surely we can imagine this as we are getting 1 over e with power of something that is 0. Okay. But of course, we cannot really making this conclusion here. We can just take this into 0. Okay. We can explain this with e or exponential graphs. So we can also think as from here, limit as x approaching negative infinity of e to the x, this will be 0. Or similarly, with limit as x approaching infinity of e with power of negative x is also 0. So because of this, that proven that limit is 0. And that's the indeterminate forms. I'm planning to give you another set of optimization, but I'm going to review a little bit, especially how we can read the graph. Okay. So after we learn on how to read the graphs, a little bit review, we're going to have some introduction on optimization, and next Friday I will review some parts and maybe continue optimization, and maybe just take some exercise. Okay. Okay, if you finish, let's look on this graph. So we have the graph of f prime. Okay. So usually, if you are observe the chapter 4.3, that is about how we can observe or analyze the curve or the graph. And sometimes the graph is not the function. Maybe it's derivative or maybe it's second derivative. Like for example, this one is the first derivative. Okay, it's the first derivative. Now, what's the key to help you at least solve this problem? Okay. Well, if you see the question, it's asking the interval decreasing, increasing. Also, we have to determine which one is the local max and local min. If you're not careful enough looking the question, when you have this point here, you are going to have, oh, this is maximum, right? Right? But this is f prime. So what's the implication of f prime? I may give you maybe 3 to 5, maybe 3 minutes to think this question, and maybe you can just draw. Maybe you can take picture first, and then you can take some notes. Maybe you take some time to maybe review your notes, because I think I already give you all the notes you need. General conclusion, the f prime to the f double prime, what's the implication? I think this one better. Sometimes when you are maybe looking for something on internet website, although we know that like information in the system, in the internet has like really a lot of items, right? You can search for anything, but you can look for if you need any explanation. You want to learn something, you can find on the internet, but sometimes you cannot find it. Do you know why? Do you know why? Why we can find? We are looking for this, but it seems that it's not there. But it's actually on the website, but it seems that you cannot find it. And that's this. I think one of the problems that students face today. Well, imagine like I think 10 or 15 years ago, there's internet, but not as fast as today, and not much information provided. But still, we can find something. But for today's generations, I think they have some problems for finding something. Even back then, like 15 years ago, there is no Google. No Google here. We are still looking from Yahoo. So Yahoo is previously Yahoo is better explorer than the Google, because Google hasn't become popular. And when people offers investment, do you want to invest in Google? People still invest in Yahoo, but then it's shifted and Google becomes large and Yahoo becomes this selling products and advertise products, like an e-shop, not really the explorer. So to find the website, to googling something, what you need to find is you need to learn how to find the correct keywords. That's what I think most of the students they need to study. So first, think on keyword. Second one, make those keywords specific. If you search too broad, you will not find what you are looking for. And then you need to check how you are going to find that item. Are you looking for some image? Are you looking for some type of file? Actually, you can filter out through Google. When you find PDF, you can filter out on Google. And I think most of the students, they didn't really think about this. So first, if you want to fasten your study, you need to at least learn something on how to find on Google. Not just Googling, but learn how to Google. Okay, that's I think the essential for today's generation. Learn how to Google. Because Google is not just typing your keywords and find it. You need to make it specified. You need to understand your topics, what you are looking for. If not, you are not going anywhere. Okay, and this f prime. Okay. The first question: what interval f is increasing? Increasing where? Someone? Any guess? Increasing?
1, 2, 3.
What?
Is it 1 to 3?
1, 2?
3.
1, 2, 3. Why not until 4? Okay, that's one mistake you made. You treat the graph as just an ordinary function. This is f prime. Okay, f prime. Okay. So first, the implication of the f prime. We have two conditions. We have positive. We have negative. What's happened if we have f prime positive? Increasing. Negative, decreasing, right? So we have, this is increase, this is decrease. Okay, now how we can know this is increasing, decreasing from the positive or negative? Do you agree that above this x all is positive. Okay, great. So let me just take this area here. This is positive, and take this area here, the green one. This is negative, which means we can clearly see that from 1 to 4 it's increasing. Okay. From 0 to 2, okay, it's not 2, it's 1. 0 to 1 decreasing. From 4 to 5 it's also decreasing. So we can write for number A that interval of increasing on 1, 4, and also 5, 6. This is also increasing. Forget to mention. And 5, 6, and decreasing on 0, 1, and 4, 5. Okay. Okay. Number B is local max, local min. So local max, local min. How do we know whether it's maximum or minimum? How do you know? If you don't know, then you draw. Just draw the illustrations that you can think of. Just draw this. So when you have the exam, you find it confusing, just draw this. Which one is max and min? This is max, right? This is min. Okay, let's just write that. So write this max, this min. And what's the implication of this curve? Implication is we have positive increasing, we have negative, right? The tangent is changing, right? So the tangent is changing from positive to negative, and from negative to positive. Do we know the positive negative from our graph? We know it's negative, positive, negative, positive. So this point is minimum. Easy, right? So minimum is when, or maybe we can write this is when x is equal one, and then we also have exchange from positive to negative at 4. Positive to negative means max. So 4 is max. So this is 4, and another one is 5. 5 is from negative to positive, which is also min. So I think just these 3x, because there are no other x's. So we finished. Okay. We finished. Finish finding the answer for increasing, decreasing, maximum, minimum. Okay. And if the questions change, not f prime, maybe f double prime, you need also to think. Okay? You need also to think how to resolve this. Or maybe if the question is asking about the concavity, maybe I add more questions. Maybe C, concavity. What does it mean? It means that you need to derive. So you need to think on second derivative. The second derivative of this curve is the derivative of the curve, right? Which means it's the tangent. So when it's going to have tangent 0, it seems that it's the inflection point. Okay, do you get my point? But you can try exercise. I think it's on your textbook, or if you cannot find, you can just take sometimes on questions related to how to read the graph. We get at least 1 or 2 questions on your exam will be about the graph. that's just a small review on a graph. Okay, now another sections that I want to introduce is the optimization. This is 4.7. So what optimizations means? Optimizations means that you will have a certain problem, you will have a certain algorithm that you need to optimize. Okay. So first, you will have a case or problem, and all the problem it will relate with critical point, in which critical point means that f prime x, at least it should be 0, or f prime x doesn't exist. But the first thing is mostly happening. And then the second one, what we can do in optimization, to understand the problem, we can draw the schematic or draw the diagram, and then naming the variables. So to help us find our functions and take it into our first derivative, we need to draw the diagram, name the variables. The third one, find correlation with all the statements in given problems, any formula you can think of, any models also. And 4, find the max or mean value. So you find f prime c equals 0. So you need to take the c and then find the value, usually. And sometimes the problem is not really complicated. Usually it's about geometric area, or maybe optimize some statement, like how to make most profit on the system, and you will be given the system and how to make it optimize. It's actually applicable in the real life. And some of the industry also using optimization a lot. Okay. So for example, let me just give you a quick question. So if 1,200 centimeter squared of material is available to make a box with a square base and open top. Open top means without a top. Okay, open top. Find the largest possible volume of the box. Okay, so imagine you are giving like a card box, and you have the area, and you need to cut and make it into box, and it should be having a square base, meaning having the same length, and then it has an open top. Okay. So we have the visuals, we have the material. Okay. So we can only make the box based on 1,200. So 1,200 is our restriction. Okay. We call this is our constraint in our case here. So maybe we can start with just drawing the box. Okay, and imagine this is without top. Okay, no top. And the base is having the same length. Let's say x, or you can name any variable you want. A, B, it's still okay. And name the other variables y, because it's not specified. All the length should be the same, so we can make different variables. Okay. And it's asking us to find the largest volume. So volume for the 3D box like this is just the area of the base multiplied with the height, right? We call this formula, for our case here, this is our optimization, right? And we have some restriction. We have restriction that 1,200 should be our constraint, the total materials that we have, the total area. The area of this shape, this box, okay, the area, we can think x, y, all this 4xy plus the x squared, that will be our area. The top is empty, right? So this will equal with x squared plus 4xy. And this is we call our constraint. Now what we are going to do is we are going to have this optimization, right? This is our terms, our formula, our relations. The first thing we can do is we need to apply our constraint inside our optimization. And later we can derive to make our critical point, in which we are going to find the maximum value, right? So let's take it into, so let's rewrite this. And let's write in terms of y. Okay. And then we are going to apply this inside the x squared y. So we are going to exchange y with this x. So we can get all one variable. Okay, all one variable. So we will have 300x minus x cubed over 4. Take derivative. Why we need to take derivative? Because we want to take, or we want to find the critical point. Okay. So to derive, the critical point will be when the v prime is equal to 0. So 300 is equal to 3x squared over 4, or x squared is 400, which means that x should be 20. Why didn't include the negative? Because we know that it should be positive. It should be positive. When x20 . Okay, when x is 20 centimeter, y is 10 centimeter. Okay, from the formula we find. So our largest volume from these findings is 20 squared multiplied by 10 is 4,000 centimeter cube. Okay. Of course, this is really simplistic problem, but I hope how we can analyze is well structured. So first, you find the formula, you find the constraint, you can draw the diagram, you name the variables, or maybe draw the diagram first, name variables, go to the formula, and then go to the constraint, and then from the constraint, you need to think how to input the constraint inside the formula, and make it. So the important thing is make it into one variable, and then solve finding the first thing, and make it equal to 0, and you will get your critical point, in which make it the maximum. We'll continue later for Friday course. And don't forget that not this Friday, 22, we will have a midterm. Okay. But that is for today's class. Okay.